talking about off-policy RL, and we will try to make it model-based RL, but we'll see how far we get. We have more of off-policy RL to come. More? No. Few logistics things. I should have sent feedback to everyone, or almost everyone. If you didn't get feedback from me on your project proposal, or you want to talk about it, just stop me after class or office hours, or just barge it to my office. Yeah, okay, let's get started. Anything else anyone needs to check before we get started? Good. All right. So kind of where we are is we got halfway through approximate dynamic programming. And today we're going to try and instantiate this into a practical algorithm, things that we use like soft actor critic. And we'll talk a little bit about open problems and frontiers of off-policy RL. And then if I go super fast, we'll get to model-based RL. Otherwise, we'll do it on Monday or Tuesday. Okay, so let's just do a little recap. We've been talking about starting from policy gradient. In policy gradient, you have the sum of rewards in the future, which is a single sample estimate, which is high variance. We said we're going to try and reduce this by trying to estimate the sum of rewards using a value function, right? So the first thing we wanted function approximation to be used to lower variance. And so the first thing we talked about was Monte Carlo estimation. The second thing we talked about is using recursive structure in this value Bellman equation. And so we had a procedure where we try to fit a value function, right? And so you sample data, you try to fit a value function by solving this dynamic programming update. And then you replace the sum of rewards in the future for a single trajectory with R plus gamma B minus B. And so what we did here is we used function approximation to lower the variance of the estimated sum of rewards in the future. And this procedure we talked about was like this dynamic programming procedure, and it's not gradient descent, right? So we'll discuss that in a second. But the point of this was that it lowers variance, but it's still on policy, right? You're still estimating value, so you still have to sample data from your policy. So when I say on policy, I mean that you have to sample data from your latest policy. You can't just use arbitrary prior data. Okay, and so we talked a little bit about this procedure, which we're going to call like your Bellman update, right? And we showed that it's a contraction. So in a tabular setting, we said this is a contraction. We worked through all of this math, but essentially we're trying to show that if you run this update, you go from VI to VI plus 1 and UI to UI plus 1. These two things get closer and their infinity function. So their max elements get closer. So eventually their max elements will be 0 apart, which means that they'll be the same. So they converge to a fixed point, and that fixed point is going to be like a true VI. Right? And so we said that in a tabular setting, this thing is a contraction, hence it converges to a fixed point, right? If you want me to like Netflix skip intro, tell me, and we'll skip it. But I think it's useful to do this, right? Okay, so we said that that's true for a tabular setting. So if everything's a table and a vector, and you're trying to do this backup, we're going to show that it converges, right? But we're in measure zero space. We're in a continuous state space action space. So in that space, we're going to say that you can't represent everything as a table, so it's an infinitely large table, right? And so instead, what we're going to do is we're going to like treat the Bellman backup. We're going to do a tabular Bellman backup for a particular batch, and then we're going to try and project it onto a function approximation, right? And so the way you can think about this graphically is that you have a bunch of points. You do a backup for them. So these are the points in your batch. You do a backup for them according to like R plus gamma B, right? And then you try to fit a function approximator to be as close as possible to R plus gamma B, right? And the reason to do this is because it's a measure zero space, you like don't have infinite numbers of points, right? So if you want to like answer what the Q value is on any of these points, you need a function approximator to do so, right? And so what we said is we're gonna do, we could think of like these after critic updates or things that even do like this iterative procedure of getting targets, doing regression, getting targets, doing regression, getting targets, doing regression. As it's essentially a combination of two operators, one which is the tabular backup, which converges, and a projection, which doesn't necessarily converge, right? So the combination of your Bellman backup and your projection may not be a contraction, hence your overall procedure may not converge, right? And so that's kind of the point to take away. But in practice, it often works well. Although there's like some challenges when you go to like really, really huge models and really huge data sets. It's still like an open area of research. Okay, good. And then we said, okay, this thing is great, but it's on policy. Right? So on policy is bad. We want to be able to use our past data or data from other experiments or data from experts or offline sources, or, if you're into Jeff Kloon's talk, you want to use data from video games or people on the internet, right? So you want to be able to do those things. So you want something that's off policy. And so to get something that's off policy, we decided to do a Bellman backup on the Q function rather than the value function. And so we said the Q function is different from the value function because the first action is different, right? And so we have this recursive update on the Q function, which is different from the value function because you have your first action coming from anywhere, and your second action is sampled from your policy, right? And so you're saying that let's kind of go slowly through this because it's going to affect everything else. But you're saying that your Q function can input an action. This can be from anywhere, including some arbitrary data set by beta. And we're saying that the policy you really want to evaluate is going to go into like the target, like the thing on the right-hand side. And so this is the policy you really want to evaluate, but you can evaluate it using SAS prime, which is drawn from any arbitrary data set, right? And so the whole point is that SAS prime tells you like the transitions of your transitions of like which S prime you transition to given a particular S and A, but you can evaluate arbitrary policies. And so the whole point is that because you have you have AP here and AP plus 1 here, they can be sampled from different policies that allows you to be off policy, right? And so one way to think about it is that, your first step, you have ST, AT, and your data set tells you which ST plus 1 you transition to. But then you sample an AT plus 1 from pi, not from the data set, right? So you sample an AT plus 1 from pi, not from pi beta, which is your data set, right? And so you could evaluate a different policy that way. And so you can kind of, if you think of it recursively, it's like this step, this step is going to come from pi beta. This step is going to come from pi, and then every step after you can get from pi. Right? So if you apply this recursively, you can evaluate how good a particular policy pi is in terms of its expected sum of rewards using data from an arbitrary data set. Right? Now, it's not completely arbitrary. You still need it to have coverage, right? So typically, there's a condition called like greedy in the limit of infinite exploration, where you just assume that you have coverage over all state action tuples. And if you don't have coverage over all state action tuples, then you're going to have like holes in your Q function. If you're going to have holes in your Q function, it's going to lead to all sorts of problems. Right? And so this whole field of offline reinforcement learning tries to deal with that. Like, imagine there was some SA where you didn't have coverage. Your function approximator can assign something crazy there, and that causes all sorts of problems, right? So it's like there's a whole field of research on trying to study the dynamics of this problem when you don't have coverage. But for the sake of this argument, we're going to assume that we have coverage. Yeah. Yeah. So there's a bunch of techniques. One of them is smoothing and like using a simpler function approximator. It doesn't go crazy. The other ones are like often using pessimism. So which is like saying you really care about the maximum value, right? So you're just going to say anything that you don't know, just like push it down, right? So you don't select those actions and you don't propagate them for it. Right. So you're just going to be really pessimistic on actions you don't know. But yeah, none of this gives you magic solutions to generalization. Like you're still going to answer things within your data set. But the nice thing about algorithms like this is that they allow you to do what you'd often call stitching. And so stitching, here's an example I like to give for any of my PhD students who are here. I talk about this often, but it's basically like, let's say you had two trajectories, ABC and DBE, right? So one trajectory was this, and another trajectory was this, right? When you're doing dynamic programming like this, you're able to find the value of policies that go this way or this way, even though they weren't in the data set, right? And that's because you're using the Markov property. So you're doing dynamic programming. And so what you can get is that you like your dynamic programming update takes like the first tuple from here and then the second tuple from here, right? So you can like recombine parts of different data sets And the point is like the tuple that this thing comes from and the stuff that this thing comes from doesn't have to be the same. So it's like the same reason that you can like do stitching between different trajectories. And that's often the reason off policy RL is really efficient, is because you can like take these two trajectories and you don't need to have exponential coverage because you can stitch them together. You just need to have like linear coverage, right? Yeah.
So if you were to do behavior cloning, and say you start at A and then you go that B.
Yes.
Would that like, why does stitching not happen there? Like
The
if
stitching does happen with behavior cloning if using Markovian policy, but the problem with behavior cloning is that it like cannot pick out what is good. Right? So like imagine you had these trajectories and your data sets were A, B, C, and D, B, E, but really the best trajectory was A, B. Like behavior cloning has no knowledge of it. Behavior cloning assumes everything is optimal. Like the assumption in behavior cloning is that your data set is optimal.
but in the Markovian setting, like once you have group data.
But let's say they're not optimal. Let's say this data was just bad data.
Okay.
You want to, if you behavior clone bad data, it's not going to give you what you want. And so you're totally right that in the Markovian setting, if I behavior clone this data, I would come this way. And then I would like choose between this and this, right? And so you're right that it would pick both paths, but you're not able to like select that you actually really want to keep going ABE and never choose ABC, right? That's the important, right? And so a lot of these, like there's a lot of new methods like decision transformers and these things, which try to essentially do what you're saying, but none of them have the benefits of dynamics programming, that they got stitched paths together. So often if you're thinking about like why off policy RL is efficient, like yes, it's off policy, you can use lots of data from before, but importantly, it can also stitch paths together, and that stitching is like is often like what gives it lots of efficiency. So okay, does that make sense? This parse. So the important thing is we can construct like a Q-learning update, right? So we're trying to convert this into an off-policy RL objective, which we'll get to next. But basically, it's going to try and enforce like this type of consistency. It's going to try and make the LHS and the RHS similar or like close in a similar way that we did for value functions. So for value functions, we did this construct targets to projection, construct targets to projection. We're going to do the same thing here. Right? Okay. And so what we're going to try and go through today is like work through a complete off policy algorithm, work through the policy updates, and then like a concrete algorithm that we can use to learn the critics. Then we'll talk about how this doesn't really work in practice and what we need to do to fix it. And then we'll think about what remains. Yeah. Okay. Any questions? Good. Okay. So the objective we're going to construct is going to look something like this, right? So it's going to say that you can think of in our last the value function thing, we said we're going to like minimize expectation v minus y yi, where yi is equal to r plus gamma v, right? And we're going to like construct a bunch of targets, do projection, construct a bunch of targets, do projection, right? We're going to do something similar here, where we're going to say, let's consider this thing to be yi, this thing to be like q, right? So we're going to like alternate between minimizing say S prime from some arbitrary data set of q minus y, and where yi is equal to r plus gamma expectation, at plus 1 from pi theta, st plus 1 or no, sorry, at plus 1 from pi theta of qp phi hat, st plus 1, at plus 1, right? So this is going to be your target, right? And then you're going to try and regress onto your target. Then you're going to update your targets. You're going to try and regress onto your target and repeat, right? So you're going to say, use my current Q value to construct a target. And then I'm going to like freeze that as a number. And I'm going to try and regress onto that number, right? And I'm going to do that for a while till my Q is good. And I'm going to replace the targets again. And then I'm going to repeat this projection procedure, right? So you can think of this as a backup. And you can think of this as a projection. Right? Same as before. So the only difference from our previous thing is rather than doing r plus gamma v, we're going to do r plus gamma expectation q, where expectation q is done with samples from pi theta, which allows you to be off policy. That's the only difference, right? Does that make sense? So like it's a little bit, so the thing you need to be a little careful about is that I've kind of written this notation as here's phi hat and here's phi. And the reason I've done that is like phi hat, you can think of this phi hat as just like an old copy of phi, right? So saying like, I'm gonna set phi hat to phi, construct a bunch of targets, and then I'm gonna freeze them and update phi to some new value, right? So phi prime. And then I'm gonna like go and update phi hat again, right? So I'm gonna have a particular Q function. I'm gonna construct targets by copying phi into phi hat, but not pass gradients to it. I'm gonna take that as numbers and then learn a new Q phi that projects onto that, and then I'm going to update the phi hat to phi, right? And so your procedure is gonna go like copy phi into phi hat, construct targets, whatever, and then like minimize your expected Q minus Y with respect to phi, and your new, and let's call this like phi star or something. This new phi star is now going to be the new phi hat, right? And you're going to repeat this over and over. Okay, so same procedure as before. We're just gonna like do this like fixed point iteration procedure where you construct targets, regress, construct targets, regress. And every time you construct new targets, you're going to take the best Q value from before and just replace that for phi hat. Right? So don't get confused by this phi hat notation. It's just like an old copy of phi. Okay, does that make sense? And the reason to do it, write it this way is just so that like when you construct it as a single objective, just don't pass gradients to it. And don't update those parameters all the time. Like keep them frozen till you finish your regression and then update. Keep them frozen till you finish your regression and update. Okay. No. Sorry, my iPad froze up. Oh no, it's still there. How do I get rid of this? Sorry guys, I have to get rid of the scribbles, otherwise we're screwed. What happened? Everything disappeared, I suppose. Okay, good. We good? Okay, wonderful. Okay, so often what you're going to do is you're going to like approximate this not with a bunch of samples from your policy. You're just going to like draw one sample from your policy. So you're just going to approximate stochastic optimization where you say you sample a batch of SA S prime from your read river, and then for every element in the batch, you're also just going to sample an A prime from your policy, right? And you're going to construct like a loss function of Q minus R plus, we call this the target Q, right? Which is like at evaluated at ST plus 1, AT plus 1. And you just try to minimize that error without passing gradients to the right hand side. And you're just going to do gradient descent on this, like use Adam. So that's going to be your objective, and you're just going to use a function approximator like a convnet or an MLP or something, depending on what your inputs are, both for Q5 and for Q. Just like data. This is not optimized for data. Like it's Python. Oh, yeah. And it's just a shorthand because like this optimization is not with respect to theta, but it's Python. Good question. Okay, so we've talked about how this may look like gradient descent, but it's not. It's fixed point iteration. And we've talked about some of the theoretical reasons, but like in practice, a lot of things are like a little bit more weird. So like, for instance, one thing that you'll notice here is that we're doing something, we technically the thing on the right-hand side, the Q function in the future should be like, there's also an expectation over future state, right? So if you look at the Bellman equation, for instance, the Bellman equation in its like pure form, right? There's like an expectation over future state, right? So like the Q function at the current time step is the reward at the current time step. plus an expectation over future states and an expectation over future actions, right? And this is important if you have things with stochastic dynamics. Often we don't have stochastic dynamics, but when you do have stochastic dynamics, the Q function has to be expectation over future states, right? And what we did in our objective is we like kind of dropped, you kind of dropped that expectation, right? So if you look at this objective, nowhere did I take an expectation over ST plus one, right? And the problem is that I like don't necessarily have I don't have like SA and like a bunch of samples from there. All I have is SA S prime one and SA S prime two, etc. Right? I don't necessarily, unless I have a simulator that I can reset. You don't actually have many different samples from the same S and A. So it's hard to even construct a future expectation. Like if I wanted to do, even if I wanted to do this thing, like it's really hard to construct that future expectation because I don't even have like a reset function that allows me to sample many different futures for the same state and action, right? So if I could reset this S and keep replaying A, then I could take many different samples of S prime, but I don't have that. And so you can show that like this is like if you thought of this as gradient descent, then you're like doing an approximation here where you're like approximating a stochastic distribution by like one sample, and that's going to be wrong, right? And so that approximation doesn't matter often in practice, but is an approximation. The other things that are problems are that if you like if you can also construct a version of this objective where you do pass the gradient to the right-hand side, right? So you just said like, I'm gonna not do this fixed point projection thing. I'm just gonna like treat this as phi and pass gradients through here and through here, right? So like just set up your objective to be, your objective could be Q minus Q phi minus R plus gamma Q phi S prime A prime. And then like take gradients of this with respect to phi, right? So you're going to pass gradients through both the left-hand side and the right-hand side. And this is like a technique you call Bellman residual minimization, because you're like looking at the Bellman residual and kind of minimize. But when you do that, it often performs extremely poorly for some of the reasons we mentioned, but also just because it like often is extremely unstable. The right-hand side moves the same time as the left-hand side moves. And so it like becomes like a really hard thing to like stabilize. And so when you're implementing these things, it'll be in homework too. Make sure not to pass the gradient to the right-hand side. It like will become very unstable. Yeah. Okay. So we've talked about Q estimation, right? So all we're going to do in Q estimation is we're going to have this procedure. We're going to sample a bunch of stuff from our data set. We're going to construct some targets. Rather this, and then we're just going to do a regression, and then we're going to construct new targets, do regression, construct new targets, do regression. That's going to give us Q phi pi, right? Now the question is, how do we use Q phi pi for improving a policy, right? So we discussed this really quick last time, but we can say that we want to find a policy pi theta that maximizes the expected value of the Q function, right? So we want to say on state sample from your data set, an action sample from pi theta, I want Q pi theta of S comma A to be as high as possible. So Q pi theta is an estimate of how good an action A is at the state S. You want to pick a policy pi that chooses the best actions according to your Q, right? And so we can just think of this as our objective, right? And if you like work through a little bit of math here, right? So we can say, we can write this as expectation S from D. Let's just optimize this with gradient descent, okay? So we're just going to say grad theta, expectation A from pi theta of Q pi S comma A, right? Now help me work through what this objective is going to look like. So if you remember our first policy gradient lecture, what are we going to do here? Reinforced it, right? Yeah, so you're just going to say, you can move this thing in here, but you can just say expectation S coming from D. And then you're going to do this like multiply and divide by pi theta trick that we did at the start, right? So we're going to say, you can write this as expectation A coming from pi theta of grad log pi theta A given S times Q pi S comma A, right? So that's just your reinforced string. So essentially, you can think of this as just being policy gradients, right? But you're just using your Q function instead of your sum of rows. And because you're off policy, the other nice thing to notice is that you don't have to do it in trajectory form. You can just like sample states from your data set. Like just like you have a big data set, just sample some states. And then you can just sample some actions and then like use this same policy gradient style update, but it doesn't have to be like tied to trajectories anymore, right? Because you're estimating Q functions from an arbitrary data set. And so you can like do this thing on arbitrary states as well, right? And so what we want to do here is we just want to like maximize the objective. We did gradient ascent with the reinforced string gives us policy gradient, but on arbitrary states. And those states can be off policy, can be arbitrary. Okay. So that's the simplest objective that we can do, right? Which is this thing right here. We said we can take the gradient here, and we can just use the reinforced string and write this as grad log by theta times Q by SA, right? Policy gradient. Is there anything else that we can do to make this like more efficient? Let me give you a hint. Like, let's say my policy pi was a Gaussian, okay? So pi theta A given S is a Gaussian of some mu theta S, sigma theta S. Like in that case, is there something that I can do to make this more efficient or lower variance? Has anyone heard the reparameterization trick? Right. So the idea behind the reparameterization trick is that if I have a sample from a Gaussian, right? Let's call like Z is my sample from mu comma sigma, right? I can say that Z is equal to mu plus sigma epsilon, where epsilon is drawn from the unit Gaussian. Yeah. And so like essentially you can say, I can just draw things from the unit Gaussian and I can kind of separate the deterministic stuff from the stochastic stuff, right? So this is equivalent to this. Right. So you can kind of think of it in like intuitively makes sense, right? Like Z is sampling from a Gaussian to go around the mean and then use the add noise, right? Scaled by the variance. And so you can say that if epsilon comes from a 0, 1, then Z is equal to mu plus sigma epsilon. Right? And so what this will allow us to do is when our policies have particular structure, you can get a more efficient update. Right? And that update is going to be, notice that we can just like use that trick here. So we're going to say that pi theta is going to be mu theta S, sigma theta S. And then our update here, we're going to try and use our trick of writing this as, I don't know why it is that, but we're going to use our trick of like this reparameterization trick in our objective here to see if we can get a lower variance grade. And so the easiest way to do this is we're going to say, take our objective, which is expectation S. And now earlier we had expectation A coming from pi theta, but now we know that we can just replace this with expectation epsilon coming from 0, 1. We can say this expectation epsilon coming from 0, 1 of Q pi S and mu plus sigma epsilon. Right? So all we did is use this reparameterization trick. We said that A is equal to Z plus A is equal to A sample from pi theta. So A is basically Z here, right? Which means that A is equal to mu theta plus epsilon times sigma theta, right? And so like the only thing that is stochastic is the epsilon, right? And so we say that the expectation is with respect to the epsilon. And you can say that the A is equal to mu theta plus sigma times epsilon, or sigma theta times epsilon. Sorry. Put the theta on the wrong. So mu theta plus sigma theta times epsilon, right? So all of the noise is captured inside epsilon, right? And so the nice thing now is when I take the gradient of this objective, neither this nor this depend on theta. So I'm like, goes all the way in, right? Which is great. So you just have S coming from D, epsilon coming from 0, 1, times grad theta of Q pi S mu theta plus epsilon sigma theta, right? Okay, now what do I do? Yeah.
That's the finish
It's also second. Did you just do like dot, element wise for?
line. Okay, so it's
Element wise for, yeah. Because we're assuming like a diagonal Gaussian. It doesn't have to be a diagonal Gaussian, but for right now it's a diagonal Gaussian. So it's an element. Okay, yes.
gradient of theta now.
So so this is one way of solving this, right? So I'm saying, let's not solve it this way at all. We're just gonna start from our original objective. So this was our original objective, right? And we just rewrote this original objective in using the retransformation.
Oh,
Right, so these are two different ways of computing the gradient, and we'll like contrast them in a second, but the way we did it here, we wrote the original objective, we multiplied and divided by pi theta, and then we like passed the gradient in that. Here what we're doing is we're rewriting pi theta as mu theta plus epsilon sigma theta, and then you're noticing the expectation does not depend on theta anymore, so you can like pass the gradient all over. Okay, so now we have this objective. How do we, like, this is not a, it's like not easy to evaluate yet. We just need to use chain rule one more time, right? So you can write this thingy, you can write it as grad A of q pi SA times grad A with respect to theta, right? Where A is equal to mu theta plus epsilon sigma theta, right? So we can say that our objective now, just simplifying, our objective is going to be, this thing is going to become expectation S coming from D, expectation epsilon coming from 0, 1 of grad A q pi SA times grad theta mu theta plus epsilon grad theta sigma theta, right? So what we did is we just separated this, the deterministic and stochastic parts. We put it all inside epsilon. So the expectation no longer depends on epsilon. You send your gradient all the way inside, and then you just use the chain rule. And so the nice part now is that unlike this version of the objective, you're actually taking the gradient of the thing inside. So if you remember our first lecture, we said like these things are much higher variance, and things like supervised learning are much lower variance. So these we often call this like the pathwise derivative or the reparameterized objective. And this is empirically often much lower variance than an objective.
But that's the cost to get this. That is simplified the representation of the policy, right? So the policy must be this.
It doesn't work for all policy classes. It doesn't work for all policy classes. Like you need to be able to separate out the deterministic and stochastic, and it's hard to do. So like for instance, if you had the policy as like a discrete thing, like it's much harder to do, like you can't do that for discrete things without using other tricks. And so like this thing is general across all policy classes. And this one is not general across every policy. No, because you're scaling, you're shifting by mu, and then you're scaling the noise by sigma. Right, so like you can show that this and this is like exactly equal. So you don't need to renormalize anything. Like it's already normalized, so it's like any Gaussian is basically centered around the mean, right? So we're saying shift to the mean, scale by the variance, or the standard deviation, and then just like you can like add it without any confusion.
Is there any case where people don't do this in practice, like where you actually don't want to have like Gaussian also class?
Yeah, people use things like diffusion policies and so on, which are hard to do, or like discrete, right? So yeah, there's lots of cases, and sometimes this works worse. There's like, you can show theoretically, that there's like situations where this thing is like higher variance actually than this thing, but in practice, in most cases, this one is lower variance. No, so the variational autoencoder uses similar trick, but our policy is still a Gaussian. Like, so in a variational autoencoder, right, like often you'll have, I'm going to erase all this. I have a typeset, but In a variational autoencoder, you often have like X going to like mu and sigma, and you like sample a Z, and this goes through some decoder and gives you X hat. And you use a similar trick so that you can like do back propagation through this kind of network, right? So it's like a similar technique, but like you're not changing any assumptions here, right? So the policy can still be a Gaussian, and so that's still fine. The important thing is that you can just like rewrite the gradient now as I replace epsilon with C at epsilon. So like you can just say you're going to sample this from the unit Gaussian, and then you're just going to use the chain rule inside. And your policy in this case is a Gaussian. There's other reparameterizable classes of functions, but not everything is reparameterized. Right. And so the trade-offs here is that this is easy to apply to a broad class of policies, very general. This is lower variance and often better empirically. So like things like soft actor critic and like most of the state-of-the-art methods will use something that does more of the reparameterization type grading, right? And so this is all like we couldn't, like one of the things you want to notice here is that here we have to take the gradient of Q with respect to A. So if you go back to our original policy grade, we couldn't even do that because we didn't, like we had an empirical sum of rewards, we didn't know the gradient, right? So you, like this term, grad AQ, you kind of don't know grad A sum of rewards, like you don't know it. And so this like is only possible when you have a function approximator that gives you this gradient. And so there's a nice part of using actor critic methods is you can change the policy update to be more effective, right? Okay, so what does all of this mean? Right, let's put this together. So you start by collecting some data with whatever policy you have. Then you learn a Q function to evaluate that policy using that data, right? So you like go through this procedure of like minimizing this objective, resetting or like decomputing the targets, minimizing, recomputing, minimizing, decomputing. And this is what you call policy evaluation, right? So it tells you how good is my policy pi. So that's what Q is. And then you do this like update on pi using this optimization, whether it's like the grad log pi version or the reparameterized version. Both of them work. And then you go back and collect more data, right? But the important thing is because it's off policy, you don't have to just use your latest data. You can keep using all the data that you've had so far. Not all of it might be useful, right? Because if it's like really far away, it's not useful in new states, but you can keep using that data, right? And so if we go back to our criteria that we wanted things that are low variance, and we wanted things that are off policy, right? And so low variance and off policy, right? And so we kind of got both of the things we wanted. And this kind of the type of method that most people would use in practice because it has both of those properties. Okay.
You should take the gradient step on pi. Is there a separate effort representing pi?
Yes. So like this update right in the previous step, right? Like is on pi, like theta is pi theta. Like those are your parameters of your policy. So like you're going to have like typically 3 networks, one which is pi theta, which is your policy. You're going to have Q phi and you're going to have Q phi. You're going to have those 3. And the more sophisticated you get, the more networks you have. And so we'll talk about it. Okay, but the nice part about this is then you can use this to like play baseball, right? This is from Peter and Charlotte back in 2003, but like with a very similar method. They use different policy classes, but a similar method, right? So yeah, so it kind of works, but we're gonna see how it doesn't work perfectly in practice, and it needs more tweaks to get it to be performed. Okay, so the procedure, like remember the procedure is just like, it's just this, you call it loop policy iteration typically, collect some data, you do policy evaluation, you do policy improvement. So your policy is pi theta, you're going to do policy evaluation, which is going to tell you Q is a measure of how good your policy is. And then you're going to do policy improvement, which is saying use your measure to like improve your policy. And then you're going to go collect more data with your policy. Policy evaluation, improvement, collect data, evaluation, improvement. This is like how most online RL procedures would work. Make sense? Okay. Good. Any questions before we do?
In the equation earlier,
Mhm.
So the term for grad Q with respect to A, right?
Yes.
So how do we take gradient of that of Q with respect to action?
Yeah, so the Q network will typically be something that takes an S and A as input and gives you a scalar output. You can just use autodiff to take, you can take autodiff with respect to the parameters or with respect to the, right? And so you just like do it with respect to the. And so what you do in practice is actually like really, really silly in that you use torch distributions and you use torch distributions dot R sample. And R sample is already going to represent Z as mu theta plus epsilon sigma theta, and it's going to allow you to pass gradients back. Right, so for anything that is reparameterizable, if you use torch dot R sample, like you don't have to do anything fancy. You just need to sample your actions using torch dot R sample, and it's going to backdrop for you. So it'll take care of that for you. So it's like much easier to implement than the grad log file. You don't have to construct any log file, anything. You just say, I'm going to sample a bunch of states from my buffer. I'm going to sample a bunch of actions from my policy using R sample. And then I'm going to like compute my loss function as Q of S comma A. Take the gradient, it'll automatically do the chain rule. Okay, makes sense? Okay, good. So this was like somewhat an academic exercise. Right? How do we go from here to an algorithm that works in practice, right? So back in, I think they first made a lot of these changes in the like early 2000s or the 90s even, but it kind of got popular in 2013 with this paper called DQN, right? And so a lot of these tricks were introduced in DQN. And there's like 4 or 5 different tricks we'll talk about to build up to like our master algorithm, right? Does anyone want to break before we keep going? Keep going? Okay, good. So the first thing we're going to do is that so far we've been talking about things that are completely batch, right? So when I say completely batch, I mean that I collect a bunch of data and then I do a lot of steps of policy evaluation. Then I do a lot of steps of policy improvement, and then I collect more data, right? So it's like in batch mode in that I run a bunch of batches. But often what works well in practice is to go from like batch mode to fully online mode. So when I say that, I mean like you go from a version where you run lots of gradient steps to just running a few gradient steps on the Q function and a few gradient steps on your policy, right? So the only thing that's different is like how many gradient steps you take, right? So earlier what we do is we say collect the data, run a bunch of policy evaluation steps, then take a bunch of, or like take several policy improvement steps, and then go and then do our update of our targets or by hats, and then repeat. What we're just going to do is we're just going to do like do it online, as in like you're going to like collect one sample at a time. So you're going to say, I'm going to collect a sample, I'm going to put it into my data set, and then I'm going to like take a step on that Bellman error. I'm going to take a step on my policy error, and then I'm going to like flip those targets from phi to phi hat, or transfer over the parameters from phi to phi hat, and then right? And so the point is that you don't have to take many gradient steps. What often works well in practice is to just do a few gradient steps, but do it more frequently, even during the process of data collection. And so you often have an asynchronous thread that's running, which is updating your parameters. You're doing sampling. Every time you do sampling, you're just going to run an update on your Q function, run an update on your policy. So you can go from batch mode to online mode. And so it's still off policy, yeah, still off policy, but you're like able to do things without like stopping for a batch. You're able to like make updates during a trajectory. And like in terms of like the empirical performance, it seems to work a lot better. Okay, but if you do that, there are some challenges that arise, right? If you do online updates. The first is that you have correlated updates. So like imagine that you're like sampling a particular trajectory, like the state, action, next state tuples you're going to get are all correlated. So it's like the updates you're going to take are not from IID data. They're just like correlated in a particular way. And the next trajectory you get is correlated in a different way, right? And so like supervised learning works when things are IID, but here your samples are correlated, and so you're going to run into trouble if you keep taking gradient updates during trajectory execution, because your samples are correlated together. Right? And so that's the first issue. And then the second issue is that, because your because you're taking gradient updates so often, and you're updating your target so often, like this whole thing is like very non-stationary, it's like changing all the time, right? And so, like in practice, if you just went from batch to online mode, it doesn't just work. You have to make some changes, right? And so this paper DQN kind of introduced two different changes, right? And the first change that they did is that they like introduced this idea of replay buffers, right? And the idea of replay buffer is like super dumb. It's just like you instantiate a big data store, they use a ring buffer. But basically you have a ring buffer where you say every time you collect data, don't just do gradient updates on your latest collected data, just like throw it into a big replay buffer, just throw it into a big data store. And whenever you do updates, you just like shuffle all that data and sample IID from that data, right? And so what you're going to do is that rather than just like sampling from your latest update, you're going to take S, A, S prime from sampling, throw it into a big ring buffer, and then sample IID from that ring buffer, right? So it's going to like decorrelate your updates because you're no longer like just taking updates on your latest batch of data. Right? And so we kind of like implicitly probably assumed this the way I kind of expose the method, but it is important. Like earlier, what people would do is like keep doing gradient updates online on the latest data. And here what they do is they throw all of it into a ring buffer, just sample IID and do the same updates. D is just like sampling from a buffer. That's it. Same here, D sampling from a buffer. And the nice part about a ring buffer is basically it's just going to overwrite the like, least recently used data. And so you're just going to wipe out the really old data. Now, often the important question that you ask with replay buffers is how do you sample from them, right? So like one way to sample from them is like completely uniformly, like just sample IID uniformly from the replay buffer. And that like kind of works. The tricky part is that it, like if there's some transitions that matter more than others, they like will not get sampled enough, right? And so like lots of like research advancements have been on like, how do you prioritize sampling from this replay buffer to be more effective? And so the paradigm is you take a bunch of transition tuples, you put it in your buffer, you can sample from it. You just need to choose your sampling strategy. So one sampling strategy is choose random numbers, sample uniformly. Another sampling strategy is you can like look at the Bellman error for different transition tuples and pick ones that have high Bellman error, right? And there's like lots of other things, but often they make a big difference in performance. And so like if you want to look these up, there's methods like prioritize experience replay. And we had a paper called Discord a few years ago, which try to like figure out more efficient ways to sample these, right? And you can almost think of like strategies of sampling the replay buffer are kind of like exploring the replay buffer, and you want to explore it. Right? And so replay buffers are good, they decorrelate things, but you need to think about sampling. Yeah.
Sure. What's the difference in TD error and target error?
TD error is the difference between Q and R plus gamma Q. Target error is like how much uncertainty you have on your target. Like if it's like, and you like try to measure epistemic uncertainty and you try to say, okay, I like really don't know if this target is accurate or not because I haven't seen it.
So it would do that with like unsampled.
Yeah, someone saw it. Okay, does that make sense? First update was this replay buffer thing. And then the second thing, what I've been talking about so far is that you have phi and phi hat. But whenever you change things, you just like copy phi into phi hat, right? You just like say, okay, I did this for a bunch of time. Now phi hat has served its purpose. I take like my new phi and I replace phi hat with my new phi. Right? The problem with that is that in practice, often it doesn't work as well because the update becomes unstable because your objective changes a lot, right? Your targets have now changed a lot and your like optimization doesn't really work because you're warm starting from the same parameters, right? And so often what you'll do is like the simplest possible thing, you just move phi hat to or phi bar to phi slowly. That should be phi hat, sorry, that's a typo. But just move phi hat to phi slowly, right? And so how do you do that? Yeah. Andy, go ahead. So you could like delay the moving updates, and that's one way people do it. The easiest possible thing you can do is just like exponential, you know, just like a silly thing. Just an exponential moving average. So you just say your tau parameter controls how much you move versus how much you stay close to the previous, right? And often this like the choice, if you wanted to tune hyperparameters of these methods, like this often matters a lot. It's going to affect how unstable your objective is. Right. So all that DQN did was it took Q learning, used it with images and Atari games, and then introduced these two ideas. The first one being replay buffers, and then the second one being target networks with exponential moving averages. Right. That's it. That makes sense? And that kind of like lets you develop a somewhat practical off-policy algorithm where you say, I'm going to collect some data, I'm going to add it to my replay buffer, and then I'm going to like asynchronously almost have a thread which samples batches from my buffer, IID, or with a prioritized sampling strategy. And you're going to like try and learn your Q function by minimizing your Bellman error, like we've talked about, right? By minimizing Bellman error, I mean like optimizing this objective. Yes? And so you like add it to the buffer, minimize Bellman error, then take a gradient step on your policy, update your target with this exponential moving average thing, collect more data, right? And so often you have like, these don't have to have, all of them don't have to happen at every step. Like you can run this every 5 steps and you can run this every so often, right? But the whole point is because it's off policy, it allows you to be flexible in how much you update things, right? And so this is an online method which avoids these two issues of correlated updates. And what's the other issue? I forgot what the other issue is. Optimization, like non-stationary objects, right? Yeah, so it kind of allows you to avoid both of those issues, right? Okay, before we go further, let's take like 2 minutes. We'll come back to keep going.
Or they think about what you mean by the sample quality.
So imagine that, so like typically when you're doing supervised learning, right, you have a big data set, and then you like sample IID from that data set, which means you take like batches arbitrarily, right?
Okay.
And which means that like those batches can be like data from you're like sampling, like each sample is independent.
Okay.
Now, if I'm like sampling things from a trajectory, like I'm like halfway down picking up this cup, like those samples are all correlated. They're all related to each other. They're dependent on each other. Right? Whereas if I had my buffer had something which like picks up a cup and like, you know, sweeps something and then pushes something and whatever. I really want to sample IID from the slice across all of them, right? So it's like these samples are all related to each other. And so it's not like they're independent, they're like related to each other because they're like sequentially connected, right? You're getting them by running the policy sequence. Right? So they're connected through the dynamics. Whereas if you like mix all your data, then it's IID, as in like the chance of getting something from this trajectory is independent.
The replay buffer mixes it.
Yeah, exactly. Replay buffer. So and
Couldn't
like
you just do that with the whole thing?
that's all the replay buffer.
Oh, okay.
Yeah.
Different than what you were saying before, like sample a bunch of stuff from the data set. Is it just?
That is
It's the same thing. It's just that you're always adding. to
Yeah,
it.
we always add it to the data set. Exactly. Okay. Keep going. Okay, so we have talked about this actor critic method, right? So we've kind of had this actor critic method where we say, hey, we have an actor, we have a critic. Actor is your policy, critic is your Q function. We're going to update our critic. We're going to use that to update our actor. And we're going to iterate between updating these two things, right? And so it's kind of, you have to maintain these two networks and you have to deal with hyperparameters for both networks together. And so a natural question we can ask is, can we just get rid of our actor? Like, does our Q function have enough information to just like get rid of the actor? Right? And so we still want to do things that optimize the sum of rewards. And so we want to find a way to get rid of our actor. How might we do that?
You get policy.
Yes, the policy.
Policies. Optimal actions.
That's right. That's right.
Because it's it could be wiggly,
Yes.
it's a good way to find the answer.
Right. So what you want to do is you want to just like take the max of the Q function, right? So you want to like solve it wiggly, but it's wiggly over states and actions, but for the policy for a particular state is just like the max. Like since
Right.
you like
A to be continuous.
yeah,
thing.
exactly.
That's-
So it can be a hard optimization, but it depends on the problem. We'll talk about why that's difficult, but if you replace phi by just max over the Q function, right? You can just like get rid of the actor, you can get rid of the like policy gradient update altogether. You just say, I'm gonna change my Bellman update a little bit. My Bellman update is no longer gonna be just the expectation over A from a policy. It's gonna be the max over A, right? So I'm saying my policy is defined as my policy is going to take actions as the max of the Q function. Yeah. And so what I can say is my Bellman update, which previously was Q minus R plus gamma Q S prime A prime, where A prime is sampled from the policy. Now I can just say this is like max over A prime, right? And so I've just removed my actor completely. And I've said that I removed my actor. And I just said, I'm going to replace my Bellman update with the max inside the objective, right? And it's probably just saying like, we have to figure out a way to like actually compute this, especially in continuous spaces. But if you wanted to get rid of the actor and you could compute this, then you're good, right? And so the point is that you can think of this as a special type of actor, which always chooses like max QSA over A. And if you can do this, then your Bellman update changes to this, and you kind of don't need any more, policy updates or anything. So the policy can be implicitly defined by your Q function, right? And if your policy is implicitly defined by your Q function, you just have one update. And so this gives you like an actor-free update, right? So your objective now, or your procedure now looks like this. You collect some data, you add it to the buffer. Now you just do this Q update with the max in there. And then that gives you your policy implicitly. And whenever you need to act in the environment, you just act according to the max Q, right? You know your Q. If you can solve that objective, then you know what your phi is going to be. And so you can kind of get rid of the actor by just having a way to like take max over your Q function, right? Now, why might this be a pain? Does it make sense? So all we did is we did the same actor critic update. We just replaced the policy with max over Q. You replace the policy with max over Q, your Bellman update becomes very similar, but rather than sampling A from phi, you just take the max, right? And if you do this, then you can also show that it has the similar properties of contraction and convergence and those kinds of things. But if you do this, then the nice part is that you kind of don't need to learn the policy. You don't have an act update. You don't have those parameters. You can just like skip the step that result. Okay, so we're going to do this, but why might it be difficult? Exploration issues in solving this guy. Oh, usually what you do is you'll like, when you're collecting data, you choose the max plus some epsilon, or you do like this epsilon greedy type exploration, which means that with the likelihood epsilon, you pick a random action, right? So yeah, that's a good point. If max, it doesn't give you exploration. So that's one issue. What are other issues that we might have?
Yeah, the max, unless it's a discrete action space.
That's right.
or-
That's right.
It's discrete. That's the-
That's right. So it's easier in discrete spaces, right? So like for problems like DQN, so DQN is an Atari game, so it takes in like an image, it goes through your network, and then what they do is they just like, rather than inputting something to the network, they just output the Q values for all the different actions. So let's say there were like 10 different actions, up, down, left, right, WASD, whatever. They're just going to output QSA1, QSA2, QSA3, blah, blah, blah. And then they're just going to take the max over this vector, right? Easy operation. But if it's a continuous space, then that's a lot trickier, right? So how might we solve this? Like, are there ways to make this like kind of easy to do?
Could you find the mode, like parameterize like the actions as a Gaussian?
That's exactly right. Yeah. So there's a paper called normalized advantage functions. And what they do is they like parameterize your Q function as a quadratic in terms of actions, and like a nonlinear function in terms of states. So like essentially what NAP does is they turn it convex. That's it. That's it. And then there's generalizations of this which make it convex, but they make it like convex in A, and it's non-convex in S, right? So like people in control do this all the time. Like, and so we just use the same trick, but it lets you like solve this maximization super quick. And the whole point is like kind of the same point as feedback linearization, right? It's like if you can still do pretty complicated things if you're like convex in actions and non-convex in states, right? And so that is what like these methods do, as Pavel nicely put it. They turn it convex. And what if you're at Google, then you don't do that kind of stuff. You just sample a bunch of shit. And so they basically use like a ton of different threads. So this is completely sampling based. And so what they do is they do like massively parallel sampling, and then they just take the max of all of those actions, right? And that's like a little biased in those kinds of things, but it's like in the limit of enough PPUs, like it works pretty good. And so there's this paper called Qt-opt, which is like really huge scale Q learning. And so this update that we talked about right here is more of what you'd call Q learning. Like Q learning will typically have the max in there, and actor critic will have an expectation and a policy. So you call this Q learning, right? And Q learning at scale is what Qt-opt is. Right? It's just like Q learning with sampling based max. Okay, so the point here is we like, okay, so what do we cover? We started from our actor critic update, right? And we said, okay, we want to go from batch to online, but there's these two problems, correlated updates and instability. We introduced replay buffers and target networks to kind of solve those problems. And then we said, okay, that's our new update where we can do things online, right? And then we said, okay, we want to get rid of the actor. So we're just going to do max over Q. And we said max over Q lets us skip one more step altogether. And this is stuff in continuous spaces, so we can either do it with sampling or convexification. Right? It's not in continuous spaces. People will still use actor critic methods more so. They're like more performant typically. But in discrete spaces, people will use Q learning. Like in discrete spaces, you don't want to deal with this like actor update and policy gradient. You just max. It's easy, right? And so
You get to see
Mhm.
this expensive
yes,
step, but doing the other network.
yes, that's right. That's right. So in like these things are nice and cute, but in practice, most people will do actor critic.
I just went
Yeah, right. But it like tends to work better with actor critic. Okay, and so this is some nice videos from this Google ARM farm where they were like learning to grasp different objects and perform like a bunch of different tasks. So they just had these robots running 24/7, just running through learning all the tasks. Yeah, that's what they call it. Yeah, it's pretty cool. And then you can also do like more precise things here, using an algorithm called HT, which is like just the particular instantiation of what we talked about. But they're learning how to do like prong insertion, just a little bit of that. And this is like from 2016 or 17, so it's gotten a lot better since then. Solved. AGI. And so okay, so far we've kind of like covered these updates that let you run things online, let you run things performantly with like large neural network models, maybe from images, right? But it still doesn't match an algorithm like PPO in asymptotic performance, right? So there's going to be some more issues that we need to fix, right? So when we just had, I would say like the methods that we discussed prior to this maybe are like 2016 or something. And then we had to like find some more fixes to kind of get this to match the performance of like an algorithm like PPO asymptotically. Like, so this is way more efficient, but often what you'll see is the curves with algorithms like DDPG will look like efficient but taper, and like PPO will go like way higher. Right. And so what we really want to do is find a way to like do that, right? And so these two issues kind of remain, and these two kind of things, if you fix them, these methods tend to perform well enough to kind of match PPO in lots of domains. There's still some gap, but much less. Right? And so the two issues we're going to talk about, the two issues we're going to talk about are overestimation bias and insufficient exploration. And so we'll cover them really quick, but come talk to me if you want to discuss them more. But the problem of overestimation bias is basically saying that optimized Q functions are often optimistic. So you can think of like, this is something, you can think of this as like a random variable, right? So when you're learning a Q function, its value is like changing all the time. And its value like may not actually converge to the expected Q value, right? The expected value of rewards in the future. And so what you're doing is you're taking like an imperfect Q function, and then you're slapping a max on it. And if you slap a max on something that has variance, you tend to overestimate because you like will not pick the expectation, you take the like the upper bound of everything, right? So it's like one way to think about it is like if your Q function is like varying a bunch, right? And if you take the expectation, it's here, but if you take the max, it's here, right? And so if I had like truly computed the average here, and then I took the max, then I'm good. But what I'm doing is I have like this noisy thing that I'm learning. And if I have this noisy thing that I'm learning, then because of like limited data or stochasticity, when I take the max, it's going to like overestimate what I actually care about, right? And so what that means is like the Q values, like these are like the true Q values. So like imagine that at some state you had like 4 different actions, right? A1, A2, A3, A4. Not a great diagram. Let's say these were the true Q values, right? Like you'll often have like some overestimation bias here, right? And so the important thing is that our Q values are not perfect, right? They're being learned and they're noisy and stochastic, and you're putting that through a max. And if you're putting that through a max, then you're going to get like overestimation. And so the way that this kind of reflects empirically is that you can see like if you did true DDPG, so true DDPG means like you like had an oracle way to compute the true Q function without the like stochasticity, you get performance that looks like that. But if you take DDPG, then you get performance that looks like this because it's like overestimating. And the problem of overestimating is like, let's say you had these 4 actions, and like this one is actually the best one, but you like overestimated this guy instead, you're just going to choose the wrong action, right? And so when you have like limited data and stochasticity, this overestimation problem causes issues because it chooses the wrong action, right? So you can think of the Q function as the expected sum of rewards when you execute different actions, but you're putting a max in there, and expectation of max is greater than max of expectation, right? And so what that's going to result in is that you're going to be overly optimistic in your Q functions, but not in a very predictable way. And so that's going to lead to you choosing the wrong actions and your performance being low. And so here's a schematic I found useful. No, I have these lines. Oh, good. Okay, so if you consider like two different actions, right? And these are like the different like values that you have for this. This is the expectation. That is the max, right? And so if you take the expectation of max versus the max of expectation, you can show that the expectation of max is going to be greater than max. It's also really easy, but generally, or always expectation of max is greater than max of expectation. And so that's going to lead to your overestimation, right? Like in your objective here, you have expectation of max, and that's going to be your problem, right? There's just a and so so Q learning is going to often overestimate the values, even though they're like the objective is unbiased in the limit, right? And so the fix is super easy, right? The fix is just instead of learning one Q function, learn like KQ functions, and then be like pessimistic with respect to all the Q functions, right? So what you'll often do is you like learn an ensemble of Q functions. So you'll consider many different Q functions. That's called the Q phi i's, right? And then instead of choosing your target as instead of choosing your target as just like the min over a particular Q function, you choose the min over all the Q functions. And so like tends to be pessimistic and kind of kill the optimism in your model, right? And so this tends to like help performance a lot. And so everything remains the same. All that you've done now is you've like when you construct your target, right? So you like do it with you take all you instantiate k different networks, okay? And you construct your target by taking the min over all of those networks. And then for each of those networks, you do regression to the same target, but each of those, they're like independent updates starting from independent places, right? It's kind of like the idea behind ensembles in deep learning. You just start them at different places, they do different things, and you can be pessimistic with respect to them. So you just say many different networks, take the min of them to construct the target, and then like and then do your update according to the min over the Q functions. That's the min over the Q. Right. And so the point is that you're like killing the optimist.
Sorry, I'm not quite sure how they're learned.
Oh, because they're initialized differently, right? So like oftentimes in ensembles, you like will initialize them differently. And so when you have like limited amounts of data, they like will behave they like extrapolate differently. And so you'll see like some of them will do this. At like points where you have lots of data, they'll match. At points where you have less data, they have some variance, and then you want to be pessimistic with respect to that variance. If you want to be like proper about it, you should like do bagging, which means that you like sample from you sample like independent batches to send to different things, but often you can send the same batches to everything and it still does different things because the networks are initialized independent. It's a good question. Yeah. Yeah. You're still learning a policy. The policy gradient point. So it's better than learning a policy because you're off policy and you're lowering variance, right? And so PPO is on policy and it has high variance estimates. But now what we're doing is we're saying we're off policy.
No, I'm saying instead of like, you're using max of these ensembles.
We're still doing actor critic stuff. So I introduced the Q learning as one way to do things. We've gone back to actor critic.
Oh.
We said we're going to do actor critic. You still have a policy network. The only thing you're changing is in your Bellman update. You just like, rather than taking like R plus gamma Q, you're going to do R plus gamma min over I of QI. Right? And so you're still doing the same actor critic thing. You're just like reducing the overestimation. Right? And so like very little changes. But I think this like really, really boosts performance, right? So you can see this was TD3, that's PPO. TD3 is basically the thing I just mentioned. This is PPO. And then if you do like DDPG, which is basically this thing without the overestimation fix, then you get something down here, right? And so like the performance like empirically like massively gets boosted just by learning a bunch of Q networks and taking the minimum. That's it. Right. The other thing that's often good to note is from a practitioner's perspective is when you're running these things, you can run way more gradient updates because you're like overestimating less. And so often if you're overestimating and you run more gradient updates, things just like blow up. But if you do minimum, then you overestimate less. Return. The walker and the ant. Yeah. Oh, sorry. They are the walker is like this bipedal like Mujoko task where you have to like walk. And ant is technically a quadruped. But it's like trying to like it's this like ball with arms on it, which is trying to run fast. So both of them are locomotion tasks. And they're like kind of they used to be the benchmarks for RL. Okay, good. So the key point to take away here is that Q learning or actor critic have overestimation bias. And if you're trying to do an actor critic method, then you just want to learn a bunch of Q functions, take the minimum over them, and that like massively helps your performance, right?
Saturation. Like.
How many networks?
Many Q.
Yeah. So in the first version of this, we just like people just did it with 2 networks, and that was fine. And in recent years, what people have done is they like upped the number of networks to like 10, and then what it allows them to do is take way more gradient updates. But totally at some level, the memory becomes unreasonable, and like I think you want to keep it between 5 and 10, no more than. Okay. And so here's some examples from my advisors group where they like learn to walk in 20 minutes with basically this algorithm. You like control overestimation by learning an ensemble and taking them in. Right? This is in the Berkeley Hills where they just like drop this robot and they try to get it to walk. Okay, pretty cool. We're not going to sit for 20 minutes, but it should start. Good. It's walking. But as compared to things where we didn't do this, like it's like an order of magnitude more efficient, and so it'll allow you to do training in the real world much more so. Like you would never run PPO in the real world. It's not efficient. Right? Okay. So let's keep going. And this is one from me a couple years ago, but we like learned how to like pick up a brush and like brush this dish. And the hand is like 16-dimensional thing, and it learns to like twirl the brush and do like stuff. But it's like, oh no, swirling the wrong way. Oh, not good. But you learn like finger gating motion and like more dexterous behavior there. Okay. There's the end. That is the end. Okay, so the first problem we talked about is overestimation bias, which is caused by taking a max of an expectation or expectation of a max, right? And when you don't have infinite samples, this leads to overestimation. The second issue that folks often saw is there's insufficient exploration. Like what Vishwas was saying was about exploration when you're trying to do this max over actions, but there's also insufficient exploration in the state space, right? And so the second issue that people tried to tackle was how do we deal with exploration and try to get things that like cover the state space, right? And so this is a graphic from my colleague Thomas, and what he was trying to do was trying to like get things to have way more coverage so that exploration becomes less of a problem. And let's skip this. But his answer was extremely simple, right? His answer was just like take the RL objective and add entropy to it, right? So this is your original RL objective, and you just add entropy to it. And so you say that you want to like maximize your expected sum of rewards, but you want to add the entropy. You want to maximize that while also maximizing the entropy of your policy, right? And so you want to say like maximize the entropy of your policy kind of forces it to explore. There's better ways to explore, but this is like a simple way. There's also like more theoretical benefits to this kind of thing from an optimization perspective. But to on policy RL, it just results in an extremely simple change to your objective, right? You can just work through the chain rule to get this. But you just like have a very simple change in objective. You just do policy grid, you just have an extra minus log pi term, right? Which is your entropy. And in off policy RL, so that is on policy RL. So you can do maxent in PPO or PRPO or any of those other things. But you can also do it in off policy RL, right? So you can do kind of the same thing, but you just will add the like entropy is just like expectation pi of minus log pi. So you just need to add a minus alpha log pi in a bunch of places. Right? For instance, in your Bellman update, you'll add a minus alpha log pi term because your reward is now reward plus alpha times minus log pi. Right? Similarly, in your policy update, you'll have your sum of rewards, but you'll have minus alpha log pi. Right? And so what this will encourage is that your policy maximize the return, but also does entropy.
So without the
Alpha
so that is something like you have to pay over time.
Yeah, so the way that people do it, is that they like find it hard to set as a constant. And so they often do like they solve it as a constrained optimization problem. And so they just say, you want to maximize reward while ensuring that the expected entropy fails in epsilon. You just construct the Lagrangian, and then you do like a dual gradient descent procedure. So you say that you can write this as a, you construct the Lagrangian dual here, or the Lagrangian here, and then you do dual gradient descent where you alternate between updates on pi and updates on alpha, right? And so like this is just Lagrange, just constructing the Lagrangian from constraint optimization, and then you're just going to achieve gradient descent on pi, gradient descent on alpha. Right? That often looks really well. It's a good question. Okay, so we're going to skip through a lot of the details, but in practice, like if you look at SAC, there's a lot of complicated stuff. It's just this. You just added minus alpha log pi to the critic and added minus alpha log pi to the end. That's it, right? And you can derive it from a more fancy perspective. We'll do that next week, or the week after. But and you can show that there's like an analog between the Bellman update and a soft Bellman update. But essentially, what it boils down to is just minus alpha log pi to the critic, minus alpha log pi to the end. And it like significantly improves performance. Okay? And so these are some examples that, you know, we did on soft critic. So you can do it for, this is for images. You can do it from images for like things like rotating this. This is the walker, like Jay was asking just now. And there's things with a hand where you're trying to like pick it up and rotate it, and then you can learn how to walk using these kinds of methods. Right? And like empirically, you can see that it tends to perform a lot better than methods that don't use entropy. Don't trust this plot too much. I think they didn't do a fair job with all of the comparisons. So like when you're updated, the PV3 SAC gap is like a little smaller. But it like what most people will do in practice now, they like use both of these things together. They use entropy and they like minimization over many networks, and that gives you the best possible performance. And so if we go back to our two tricks that made this thing work, one is to fix overestimation bias by training constant networks, and the second is to add entropy to deal with insufficient exploration, right? And so let's see. The whole point here is that we can then get these algorithms to like perform pretty well, well enough that you can like significantly outperform PPO in terms of like sample efficiency and kind of match performance in many domains. I'll skip the frontiers because we're a little out of time, but go through my slides. There's lots of like research questions that you might find interesting. Maybe the last thing I'll leave off on is like what makes off-policy RL hard is a combination of three different things, right? So the first is function approximation, as we talked about. When you have function approximation, things are not contractions. The second is bootstrapping. So by bootstrapping, I mean that like you're using this thing to construct targets to redress this thing. Right? And the third is that you're being off policy, right? And so when you have a combination of these three things, that becomes the big problem. And that's what they call it the deadly triad. But it's basically just these three things, right? And so empirically, you'll see that like if you did something without any of these tricks and you just like kind of look at the combination of all of these things, like 61% of the runs would deviate or diverge. And so when you have a combination of these three problems, you kind of have lots of divergence issues. And so like a lot of the things we discussed try to fix some of these problems, but that's what fundamentally makes off policy hard. And if you're excited, you should work through this particular example. It's like a really simple example, two states. One of them is like a linear function approximator. The parameter is W. The features of state one are 1, features of state 2 are 2. And if you like work through the Q-learning update on this, you'll see that it like diverges, right? Which is like, it shouldn't, it's silly. But if you combine function approximation, even linear, with off-policiness and bootstrapping, it tends to like lead to divergence. Okay, good. We'll do model-based RL on Tuesday, and discussions next Thursday. Okay, good. Thank you.